Hello everybody, my name is Ionut Balosin and today we are going to discuss about bytecode, about the process of interpreting the bytecode during the runtime inside the JVM and how to get into the native code. Here it are some words about me. My name is Ionut Balosin. As I've told you, I'm tech lead at Luxoft. I have overall 8 years of Java experience. The last 3 are on Java financial applications. And as well, I'm the author of Java Performance and Tuning course, a course which is available on the luxoft.training.com website. It's the training website. This is the agenda for today. We will start by understanding the bytecode. We will discuss about how to disassemble the bytecode in order to become in a human readable form, how the bytecode is executed during the runtime in regards with the interpreter and the just-in-time compiler, how to check the native code that was generated based on the bytecode, and we'll run some case studies. This is mainly in a nutshell what we are going to discuss in the current presentation. Let's start by mentioning some of important features for a Java virtual machine. The first one is that Java virtual machine is a process. It means that inside an operating system you can have many processes, many virtual machine processes. Another one is that Java virtual machine is stack-based. Stack-based means, in fact, that all the arithmetic operations are managed into a last-in, first-out fashion. We just have to pop and push data into the stack and from the stack in order to do all the things. The advantage of this model, stack-based approach, is that, for example, we don't have to worry about the address of the operand itself, because once we do a push into the stack, we just get it. It's out of the box. On the other side, we have register-based virtual machine, but in case of Java, it's not the case. Java is a stack-based virtual machine. Another thing is that at the code level, we don't have any kind of memory reference like in C or C++ where there are pointers. We have only symbolic references. Having this feature in mind, let's continue further. Java C. Java C it's mainly the tool that generates based on the source code, it generates the bytecode. At the bytecode level, there are many instructions. They are called opcodes, and each opcode is represented through a single byte. That's why this intermediate representation of the code is called bytecode, because all opcode it's represented, it's stored through a single byte. In practice, there are about 200 bytecode instructions which are intensively used. More than that, these opcodes are organized in families, and we will discuss in a few slides about this. At the bytecode level, we don't have any access to direct memory. We work only with symbolic references. And another thing is that at the bytecode level, we don't have any high-level features presented or that appear at the source code. For example, all the comments are erased and the for and while loops are translated into jump instructions like go-to instructions. On the other side, we have the Java P. Java P is really a nice and useful command line. It's included in the JTK distribution and helps developers to disassemble the code. What it means, in fact, we have the bytecode already generated, and through the Java P, we get the disassembled form of it. What it means, it's a human understandable form of the bytecode, because by just opening the class file, we can't figure out anything. So that's why we have to move it, to translate it into this disassembled code. And by default, the disassembled code has -c parameter and path to the class, and it shows only public and default methods. If you are using, for example, an ED, I recommend you for Eclipse bytecode visualizer. We will see it during this presentation. And if you are using IntelliJ IDEA, there is another one. It's called ASM bytecode outline. Mainly the process that I've discussed look like this. So we have the source code over here, which is pure Java. We call the Java C, which is the compiler, and we get the bytecode. The bytecode, this is, if we are opening the .class file, this is the bytecode. This is the shape of it. In order to understand what is it in fact, what are the instructions inside it, we have to disassemble it. And the disassembling part is done by Java P. After the disassembling, it looks like this. So it has, these are the instructions, those opcodes, and we'll discuss how it is in fact, what it means, each of them. Let's move to the next slide. Into this slide because we see here this .class file contains a lot of characters. Let's say not in a human understandable form, but this class has a specific format, and this format is described here. In fact, it's a C structure because the HotSpot implementation is based on C, and it starts with a magic. This magic is a keyword spread across the 4 bytes into the bytecode, into the .class, and it has a predefined value, and this value is coffee babe. This is like an identifier when a class loader loads a file. Let's say if that file, that bytecode, do not start with coffee babe, is not valid anymore, and the process is dropped. The next two are minor and major version. Minor and major version, each of them are across 2 bytes, and they are for backwards compatibility. For example, in my case, this is the minor 00, and this is the major. This major is in fact 52 translated into decimal, and it means this bytecode is compliant with JDK 1.8. If I'm going to run this class against an earlier version, it won't work, and I'll have an unsupported class version error. That's why the magic and the minor number, that's why the major and the minor number are really important. The next two is the constant pool, and for getting into the constant pool, I will slightly change the slide and we'll get back to the previous one. The constant pool, it's in fact an ordered set of constants used by the type, for example, string, literals, integers, floating points, floating constant, and symbolic references. All the entrances in this runtime constant pool are managed by an index. Every entrance is on 2 bytes. We have all this on 2 bytes. And the purpose of the runtime constant pool is that it plays a really important role in the process of dynamic linkage during the runtime, because at the source code level, we don't have any virtual memory address, and we work only with symbolic references. And for resolving those symbolic references during the runtime, the constant pool is used. It's mainly a symbol table that helps the JVM, the hotspot itself, to grab the actual implementation from the virtual memory of that object. This is the runtime constant pool. Next, at the class file, we see we have some access flags. That's mainly some access flags for the class itself, like access modifiers, if it is static, final, and so on. This and superclass are some indexes into the runtime constant pool corresponding to the current class and to the superclass. Interfaces, these structures are mainly to describe the interfaces that the current class implements. Fields are for all the fields or the fields that are contained into this class. Methods are all the methods defined into this class. And here at the end, we see some attributes These attributes mainly describe, for example, the exceptions table. We'll see what is an exception table, and as well the inner classes and so on. So mainly this is the structure of a .class file once we got the bytecode based on the Java. Now let's move on and let's try to understand better the bytecode, because until now we were focused on the dot class, but now let's move further and trying to understand the bytecode itself. I said that the bytecode is organized in families. Here we have three important family categories. I choose them. For example, it's one category. It's called invocation opcodes. Another one is for arithmetic opcodes, and another one is for load and store. Of course, there are more, but those three are more important. In the invocation opcodes category, we have opcodes like invoke interface. Every time we are saying, I want to invoke this method, interface.method, it's translated into an invoke interface. Every time when I'm trying to invoke, for example, to call a non-overreadable instance method, this is translated into an invoke special. A non-overreadable instance method, it's mainly either a private method or could be a constructor. Invoke virtual. Invoke virtual, it's a regular overreadable instance. It's a virtual method, in fact, a method that once declared in the parent class, and that class is enhanced, it's extended, it could be overridden. And we'll discuss a little bit more about this invoke virtual, because during the runtime, there are a lot of improvements around this invoke virtual in order to get the right implementation. Invoke static, it's mainly for calling static methods, and invoke dynamic, it's for dynamic method invocations. For example, the lambdas added by Java 8, and the JavaScript, which is in fact compiled and executed by the JavaScript engine. That could be either Rhino or Nashorn in the last implementations. We have as well arithmetic opcodes. Into this category, I've choose add for addition, sub for subtract, div for division, and mul for multiply. All these are for arithmetic operations. And we have another category, which is load and store. Load. What does load do? For example, when it says load, the load gets a value from a local variable array into a stack. Because I said in the beginning, the JVM it's built on a stack-based manner. We are using during the runtime push and pop, into the stack. But what is this local variable array? This local variable array, it's an array that contains on the first position, if the method is non-static, it contains this, a reference to the current instance, and right after that are the method arguments, for example, in this case, A and B, and right after that, starting with the third index, in our case, are all the fields declared locally into this method. So it's mainly an array containing all the fields at the method level. LDC, it mainly says that I'm going to load a constant from the constant pool and I'm going to put it into the stack. Store, it's like the opposite for load. When I say store, I'm getting a value from the stack, I'm removing it and I'm putting it back into the local variable array. And that mainly duplicates the top of the stack. Why we need this operator? Because in case of some invocation opcodes, for example, invoke virtual, and invoke special consumes the top of the stack. And once we are getting back from that call, the reference for it, it's lost. And that's why we have to duplicate the top of the stack. Here it's mainly our initial method. It's really a simple method. It adds two numbers. It does the sum of them. It prints the sum and returns it. And here it's the bytecode after we disassemble it. At the bytecode level, as we discussed, we have these opcodes: load, add, store, invoke, virtual, return are the opcodes. What is this I? I stands for integer, and this 1, 2, and 3 are mainly indexes into the local variable array. We'll show you right after this slide how it works. But up to now, keep in mind that I'm going to load into the stack two integers, I'm going to add them, and I'm going to push back the result, the sum of them, into the local variable array. So this 3, it's an index into the local variable array. What is this 73? We have another case when, especially for these calls like invoke virtuals, invoke static, invoke interface, and so on, we have a reference into the runtime constant pool. So mainly when we have opcode space something, a number or the figure, that number it's a reference, it's an index into the runtime constant pool. And when we have opcode underscore something, a number, that number it's a reference, it's an index into the local variable array. But let's see how it works in fact, and what is a stack frame. Every method which is in fact invoked at that time, a stack frame is created, and that stack frame is added to the current thread. So if I'm calling this add method, a stack frame is created with the local variable array and the operand stack, and it's added to the current thread that invoked that method. We discussed briefly before what is a local variable array, and I explained that the local variable array, it's an array that contains all the variables, including arguments in it, and an operand stack. Operand stack, it's really important because it acts like a workspace in order to achieve all our operations inside this method, in fact. And let's take this simple example. Let's see how it works. So I have this add method that receives A and B as arguments, and this is the bytecode that does the sum. The first one is I'm going to the first opcode is I'm going to load this integer into the stack, but where I load it from? I load it from the index 1 from the local variable array. So here it is pushed into the stack. The second one is I load 2. It's exactly the same case as the previous one, but this time we are loading from the local variable array from the second position. Now we have to add them. Once I call iadd, the top of the stack it's in fact erased, and another the add it's pushed with the result of this operation. So now I have into the operand stack the sum. What next? I have to store in fact this sum, and for that I call iStore underscore free, which means in fact the top of the stack will be moved back into the local variable array at the index 3. This is mainly how it works. In fact, at the bytecode level, this case of bytecode interpretation. I took a really simple example to be easier to explain and understand. But let's move further, because this is one case, and we have another case where we call entries into the runtime constant pool, because we are going, of course, we did here the sum, but we have to call the print method. And what happens this time when I'm saying print the sum, the bytecode looks like this. It's an invoke virtual. I'm calling a virtual method, and I'm going to resolve that virtual method based on the runtime constant pool, and more precisely, I'm going to resolve it based on the 73 entry in the runtime constant pool. What is this runtime constant pool entry at the 73 position? It's in fact a method ref. A method ref, it says that, okay, at this entry, I have a method reference. For resolving it, I'm going to switch to another runtime constant pool entry, which is at the first position, and the first position it's resolved into the second one, because the first position it's in fact a class. And if I have to search and to look for the name of that class, I'm going to move to the second position, and I'm going to be here. So up to now, I see that I'm going to call a virtual method that belongs to the Java psample class. But I have also to look and to search for the name and the type of that method I'm going to call. And for that one, I'm going to resolve that based on the 74 entry into the runtime constant pool. And at this entry, I have a name and a type. The name and the type, it means mainly the method name and the descriptor of it. And to search for the name of the method, I'm going to switch into the 29th entry into the runtime constant pool. And now I see that I have a print. This is the name of the method. And right after that, in the 30 entry, I have the descriptor, which means, in fact, the print method. It's a void method that receives an integer. So this is the way of how the print method, a symbolic reference is resolved based on the runtime constant pool, and the actual implementation and the actual method itself is resolved. Let's take a really useful example of how the Java virtual machine handles the exceptions. I chose this method, which is called reminder. It has two arguments. The first one is dividend and the second one is divisor. And inside it, I have to return the modulo operation of these two, dividend modulo divisor. And if an error occurs, I have to catch that error and I have to try divide it by zero exception. This is my user-defined exception. How the bytecode looks, in fact. The bytecode looks like this. If I have to compile it and disassemble it, I get this piece of the bytecode. And inside this piece of the bytecode, I see the exception table. It is really useful in case when, let's say, an exception is thrown inside this method. The first thing that the JVM does at the runtime, it's in fact to inspect the exception table. And based on the place where the exception raised, I mean, if the exception was raised between this 0 and 3 indexes, and if my exception that was raised is this type, I'm going to handle it. I'm going to switch the execution to the fourth position, and I'm going to continue from there. What happens, for example, if I don't see a match into the exception table? If I don't see the match into the exception table, the stack frame is discarded from the stack itself, and the exception is propagated back to the caller. And the exception table inside the caller code it's looked. And if there is not an exception found and a handler for it, it is propagated back and back and back. This is how the exception mechanism works during the runtime inside the JVM. Let's move on and see how we are working with the Java P command, because it's kindly a useful command if you are trying to disassemble and to play a bit with the disassemble code. I told you that the Java P comes with the JDK distribution. It by default prints all the public and the default methods, and you have to add the -c. If you try to see everything like constant pool, exception table, and so on, you should run it with minus verbose. But let's take this case. Let me show you first the Java P sample class. In the Java P sample class, we have here the method that we discussed about, the reminder method. We have the add method and we have the print method. Pretty simple methods. And we have as well our custom defined exception. And let's see how I can get the disassembled bytecode based on the Java P. I'm typing Java P -c and the path to the Java P sample itself, and I'm getting this. Okay, or you can type, for example, with minus verbose option, and you are getting more and more information. What I'm trying to do, because this is not a really fancy way of seeing the bytecode, I'm going to switch into the Eclipse, and I'm going to let you know I'm using the bytecode visualizer, the plugin I told you about in the slides. And with this bytecode visualizer, I will in fact disassemble my Java P, just double click on it, and it is automatically disassembled once you have the plugin installed. And here you can see the runtime constant pool with all these structures and all the information in regards with each structure. We see here our method, the reminder method. We see the exception table. We see the print method, in fact, which relies on the sys.out. Here you see the sys.out translation into the bytecode. We have the add method and so on. So mainly this is the bytecode. It's useful in situations, for example, and we try to see, for example, if you are curious to see how a for or a while or a synchronized are implemented at the bytecode level. Okay. Not this one, sorry. I'm going to continue my presentation. So this was the first part in regards with the bytecode and how to disassemble it. And I gave you some tips some clues in order to understand it based on some real simple scenarios. Now I'm going to switch and move further into the execution engine. Because this is the main important part of the presentation, in fact. Just to let you know, when the hotspot was created, the guy that developed and started to work on it had in mind two rationals. The first one was weak generational hypothesis, which means that all the objects that are created, and most of them, the majority of them, become unreachable soon, which means that once I've created an object, I expect that object to be eligible for the garbage collector. And this approach, this guideline influenced the way that they designed the memory split and the way of the garbage collector. In regards with that, we have many heap areas like young generation with Eden and the two survivors. We have the tenured zone, and we have the perm or the meta space. And of course, we have several garbage collectors that are compliant with this memory split. But this is another topic. I won't insist too much on it. The topic that is interesting for our presentation is the execution engine. And in regards with that, there is another rationale saying that only during the runtime, the JVM can take the best optimizations and the decisions in order to highly optimize the code. And this guideline influenced the way of how the hotspot works, in fact. And inside the hotspot, we have, for the execution engine, we have the interpreter and we have the just-in-time compiler. For here in the right into this picture, we see the overall process of how it looks like and how it works. At the beginning, we have the source code, which is mainly our .java class. We have to compile it. We get the bytecode. But what happens after we have the bytecode? We discussed into the previous slides about the structure of the bytecode, how the bytecode looks like, but how is it in fact handled by the JVM during the runtime. Initially, we have a class loader that loads that bytecode, and once a method is being invoked, we have into the execution engine, we have the bytecode interpreter and just-in-time compiler. Just one sec. The bytecode interpreter interprets the code in a way that I've described you based on the operand stack. But what is this just-in-time compiler? The just-in-time compiler, it does the real compilation, it translates, and it does a step further. Starting with the bytecode, it tries to compile it and into the native code in order to run faster and faster. And once it is compiled, there is a lot of profiling and there are a lot of optimizations. All the compiled code is stored into the code cache. There is a dedicated memory area like heap, like permgen, like metaspace, which is called code cache. Into this code cache, we have only compiled code, and the code cache has a different policy for cleaning the code. It has nothing to do with the other memory areas into the hotspot. Now let's talk a bit about the interpreter. And I'll explain you why they chose this way of interpreting first the code and why not they didn't compile all the things ahead. The rationale was, of course, during the runtime, there can be the best optimizations, but if I'm trying to start the JVM and if I'm trying to compile all the code, I might get a worse speed up for the hotspot itself. And it doesn't make sense to compile all these methods because it takes time and maybe only few of them are really used. And the thing is that only the methods that are intensively used, that are frequently used, and only those that reaches an invocation threshold, those methods become hotspot and they are compiled. That's why we have the hotspot name for the JVM, because of this hotspot are mainly methods that are quite intensively used inside the JVM during the runtime. And the hotspot, the just-in-time compiler is focused only on those methods. We have a JVM argument in order to influence this invocation threshold, it's called compile threshold. It's mainly the number of invocations or branches before to compile a method. Once that method reaches this threshold, it gets compiled and it's switched into the native code. In the world of the just-in-time compiler, in the world of just-in-time compiler, we have many shapes. We have the first shape. It's minus client. It's the client just-in-time compiler. It's the C1 compiler. We have the second one, which is called the server compiler, and we have a mixed mode, which is called tiered compiler. So mainly, let's see how each of them are used for and what are the advantages or disadvantages for each. The client compiler, it's the simplest way of compiling things during the runtime into the hotspot. Why? Because we are getting fast code generation of acceptable quality, which means that once I start the JVM, I might have better chances to get native code sooner than if I start the JVM, the hotspot in the server mode. And this client compiler shape does only rock solid and proved optimizations. What it means, in fact, that the compiler during the runtime do not optimize something if it is not sure about that. We'll see in regards with the, by comparison, the server, the C2 does a lot of aggressive optimizations. Other thing is that the compiler do not need a profiler. Once it gets the bytecode transformed into the native code, it doesn't need a profiler in order to profile the native code and to improve it more and more. And that threshold that I discussed about, it's in case of the client, it's 1500, 1.k invocations. The server one, it's mainly optimized for, it's mainly in charge with highly optimized code because it does a lot of aggressive and speculative optimizations. It means it does an optimization only if it's not able to prove it. For example, I do this optimization, I put that optimization under, let's say, check condition, and if further, afterwards, that check condition is not valid, I have to decompile and switch back into the interpreter. If that check condition is valid, it's fine, I'm going to continue. This compiler, the C2 compiler, needs a profiler. It does a lot of profiling during the runtime, and for that, a method needs a higher threshold in order to be compiled in the server mode. We have as well a mixture between these two, the server and the client, which is called tiered compilation. In the tier compilation, we have many levels from 0 to 4. The first level is the interpreter. It's by default the level that when the JVM starts. It starts in the interpreter way. Right after that, we are going to switch into the C1, and during the C1 phase, we have many steps. C1 without profiling, C1 with basing profiling, C1 with full profiling. And right after that, after we are going through all of this, we are getting into the C2. This is highly advanced way of optimizing the code. Here in the right, we have the overall process. We have the source code, it becomes the bytecode, and it becomes, it's translated only by the compiling to the native code. The interpreter could not do and create the native code. We have in the compilers world, we have the just-in-time compilers, and this AOT stands for ahead of time compilation. This ahead of time compilation, it mainly says, do this compilation offline. Once I'm done with the compilation, include all the things compiled into a package and run it. It's the case for the J9 JVM, or for example, the last Android distribution was switched from just-in-time compilation to ahead-of-time compilation. Why? Because in the mobiles world, I don't need to wait a certain moment of times in order to have better performance during the runtime. I don't want to have to wait after some warm-up phases in order to get better improvement. Once I start the virtual machine, I have to benefit of the performance. And that's why in the latest distribution, the Lollipop one, they switch into the ahead-of-time compilation. Here, into this diagram, we have the process that we discussed. We have the bytecode, we have the profile that in fact profiles all the native code in order to improve it. We have the optimizer, and here is one important thing, because in this process of moving from the bytecode into the native code, we have an intermediate representation of the bytecode. The things are a little bit more complicated, and I won't go into too many details, But just for your information, the bytecode is translated into an intermediate representation, which should be in a static single assignment form. It's a normalized form. Based on that form, it is optimized and the code is generated. This is how it works during the runtime. Now let's see some of the just-in-time compiler optimizations, because we discussed about how it works, but let's see how it does in fact. Just one sec. The just-in-time compiler does a really bunch of optimizations. Here in these slides, I am going to present just more important ones, just a few of them. The first one is called dynamic devirtualization. In the server mode especially, the compiler loves to do this dynamic devirtualization. What it means, in fact, imagine we have a parent class which is called base. And we have another class which is called child that extends our base class. We declared at the base class level my method, let's call it foo, but we overridden it into the child. And at the runtime, I call my parent class .foo, but the instance itself, it's an instance of the child class. What the compiler does, because this process of finding the actual implementation for that virtual method, it's costly. In fact, we have to devirtualize it, and in case when there is only one implementation, just as it was in our case, because we have one parent and one child, this call become a monomorphic call. Having this in the just-in-time compiler, having this information, it's really easy for the next invocation to invoke a monomorphic call, because he knows exactly what is the implementation, is instead of searching for a virtual method and finding the actual bytecode or native code. Dynamic devirtualization, it's another let's say optimization. What it does, after a while, if I have another extension for my base class, and of course the method foo, it's also overridden into that extension, and I'm calling the foo from the method from the second implementation of my parent class. What does the compiler? The compiler says, okay, what I've done before, it's not anymore valid, because I thought it's a monomorphic call, but now I see there is another implementation for my method, and it has to de-optimize what was optimized previously and maybe re-optimize it later on. And when we have, in this case, when we have two method implementations into two separate children classes, we have a bimorphic call. Intrinsics, it's another interesting kind of optimization during the runtime done by just-in-time compiler. Intrinsics are mainly optimizations done in regards with the CPU and in regards with the architecture, the hardware architecture itself. And the best example in this case is compare and swap operation, because the compare and swap operation, it's mainly, in most of the cases, implemented at the hardware level. I don't think if there are few cases when nowadays compare and swap operation is not implemented into the hardware. And the just-in-time compiler should rely on the hardware implementation. It is not needed anymore to inline the method itself, but insert the best native code. Other examples are the string equals method, all the methods from math class, system array copy, object hash code, and so on. If you open, for example, the concurrent atomic package from the Java, we see here a lot of compare and swap operations for atomic integer and so on. Another optimization, it's called method inlining. Method inlining, it's mainly an optimization in order to reduce the overhead of pushing and popping on the stack. Here, if I have this get interest rate method, and inside it I have to call another method, it makes sense to inline the code from this method and copy it into the caller method. This way I bypass the stack overhead. Another kind of the optimization, it's called loop unrolling. Loop unrolling, it's mainly in the server mode. For example, we have this loop for 1 to 100 in our case, and we do inside it, we do compute, 100 times compute. This loop unrolling, it's the way of optimizing this loop, and the optimized shape of it will look like this. Why? Because the loop and while and all these cycles, loop cycles, are implemented based on the jump instructions, and the jump instructions are really costly, and that's why we have to decrease the number of the jump instructions in order to benefit of more performance during the runtime. We have another kind of optimization, which is called null check elimination. This, in fact, eliminates all unreachable null code branches. For example, if I see here Java performance and tuning, which I'm sure that it's not null, I have to drop this. I'm pretty sure I have to drop it. It doesn't make sense to do this check anymore. Another implementation is lock eliding or lock removal. For example, I have this foo method, and inside the foo method I have a synchronized, and the synchronized is mainly on the list. What happens? This method has a stack frame when it is invoked, and that stack frame it's added to the current thread. And each thread that will call this foo method will run it into his local stack frame. So it doesn't make sense to have here synchronized, because it's only the current thread that reaches the synchronized keyword. Apart that, just a few notice on the synchronized keyword. The synchronized in the earlier version of the hotspot, it was really costly. Starting with the 5th or much better into the 6th version, the synchronized and the way it is implemented, it was really improved, because the synchronized, in fact, it's implemented to mutexes, to conditional variables, to compare and swap, and so on. So it's really costly. So in order to avoid the synchronized, which is meaningless, is nonsense to have it, the compiler will remove it. Lock versioning, it's another type of optimization. It's opposite to the synchronized elimination. It merges the synchronized blocks in order to not invoke synchronized too many times, because the synchronized is costly. And if we have like this sequence of critical sections, this and this, and between those two, we don't have any critical section, the compiler decides that those three must be merged into this critical section. Another interesting optimization is escape analysis. Escape analysis, it means it doesn't make sense to create an instance of an object and to push it on the heap if the scope of the object is local. Imagine we have, for example, a method and a loop inside that method, and inside that method we create a plenty of instances. Those instances have a local scope, and the just-in-time compiler decides during the runtime, based on the scope object, if it is local or not, to allocate them on the stack. By allocating the instances of objects into the stack, the number of DC cycles are prevented, and of course the heap occupancies as well, because once the stack frame it's dropped, once the stack frame it's we have a pop, all these instances are removed. The escape analysis is enabled by default, starting with the JTK Java 1.6 update 23. Here are a bunch of the arguments used in regards with what we have discussed until now. The first one is if we are trying to deactivate the compiler, we have to use this Java compiler equals none. In this way, during the runtime, our HotSpot JVM will run into using only the interpreter. We have for enabling the client and the server, we have this minus client and minus server. For activating the tire compilation, we have this tire compilation. For seeing the compilation into the console, we have to switch and to add when the JVM starts print compilation flag. To see all the inlinings, all the code that is inlined, we have to choose print inlining. To see the number of time spent in the compilation phases themselves, we have to take CI time. And the next two arguments are for inlining. In order to inline a piece of code, it couldn't be inline if it is too big, for example. And to control that inline size, which is specified in bytes, we have this max inline size. The max inline size doesn't take a look at the invocation count. It is not correlated with the method threshold. On the other side, we have frequent inline size, which is based, in fact, on the invocation count of the method. Here, it's about the assembly code, because we discussed how we reach at the point where we benefit of the native code, but how we can see it. It's not, this is not coming by default with the HotSpot JVM. We have to do some additional steps in order to really see the assembly code. Here it's really a good guideline in order to build this library. This library, sorry, is the library that is used for seeing the assembly code, and here it's a really good documentation in order to build it on specific platform. And after you get the shared objects, the SO or DLL, it depends on your operating system. You just have to copy it under the GRE environment. And when you start the JVM, don't forget to put these arguments, unlock diagnostic VM options, and print assembly. And this way you activate the assembly, and the assembly it's printed into the console, and you can see it. You can see all the things that were compiled. Now it's time for the case study, and I organized the case study in two main sections. The first one, I'm getting to describe the time access for a program which uses only direct field access. It doesn't use getter and setter in interpreted versus compiled way. And the second part is in regards with the virtual calls and the speed of inlining the virtual calls when they are monomorphic, bimorphic, and polymorphic. Monomorphic, one implementation; bimorphic, two implementation; and polymorphic or megamorphic are when there are multiple implementations for the same virtual method. And at the end of the presentation, at the end of the case study, I will see you a really useful tool which is called JIT Watch. Based on it, you can easily spot the assembly code. Let's start with the first test case. I'm going to open the Eclipse. Let's close this. Okay, let me describe in a few words how it does. We have to calculate a sum, for example, based on the number of iterations, and this sum is in fact calculated using an additional object, and the access of the instances for this object is done through the getter and the setter. And on the other side, I have the same implementation, but sorry, just close this. On the other side, we have just the same implementation. So I'm doing the same sum from 0 to number of iterations, but using an instance, this object instance with direct field access. So the only difference between these two implementations are the way we are retrieving the counter itself. Once is retrieved to getter and setter, once it's retrieved to direct access. And let's see the speed between these two scenarios, which one is faster, and we'll discuss why. Okay, let's run it. It's this one. No, sorry. One more sec. Let's call this one. Okay, so no more arguments. I'm going to run it. And during the runtime, I'm going to vary the number of iterations. So I have a bunch of iterations, and I'm calling into a loop based on the iterations, and I'm computing the time spent. And let's see what we've got. So here, the first line, it says mainly after the first 100 iterations, I have, in case of direct field access, I have an iteration that took 7,000 nanoseconds, which means, in fact, 7 milliseconds, and in this case, with the getter and setter access, the iteration took slightly less. Anyway, this kind of iterations are normally called warm-up iterations. Every time you do performance testing, and all the things, don't rely on them because they are not relevant. In the beginning, we have a lot of noisy code that is not relevant in our test scenarios. What we have to look at is only the last bunch of iterations, because during these iterations, our code reach a steady phase, and we can rely on the time. And we can see here that even if the figures, the time spent per iteration, was really different in the beginning, due to the way of the hotspot optimized the bytecode, and the way that at the beginning we benefit of the native code, which is highly optimized, we got the same time access for the getter and the setter. Let's see now what we get if we in fact disable the compiler and we are running only in the interpreter mode. In this way, we'll see, of course, much improvement, but the time is not the same. In the previous run, we encountered about 1 nanosecond per each iteration, but now we have around 19 or 40. The thing is that the difference is that here we don't have native code. All this was run based on the bytecode because we disabled, the just-in-time compiler. So the benefit of having this just-in-time compiler, it's mainly, from the developer perspective, it's mainly for the code to be performant during the runtime. On the other way, we have the second example. So we understood better the role of the interpreter and the compiled. We saw, based on this really simple scenario, the benefits and the differences between those two. Let's move to the second test case, which is in regards to virtual methods. And let me explain you a bit. Yes, this is. Let me explain you a bit the program itself. So I have this parent class which is called shape, and the shape has it's an abstract class, and it has 3 implementations. Each implementation has method area with custom implementation, because the method area is an abstract one. And we see we have square with this implementation for the method area. We have rectangle with this implementation for the method area. And we see right triangle, the third implementation for our shape, which has a total different algorithm of getting the area. And what I'm trying to do is I'm going to create 3 shape instances, one of type square, or one of type rectangle, one one of type right triangle, and I'm going to do a test with each of them. What I'm doing into this test, it's mainly I'm calling the area, which does the area, and I measure the time from the beginning to the end. I convert the time into the seconds, and as well I'm counting how an iteration took. And I have two bunch of tests. I have the first bunch, which mainly it's called warm-up phase. And right after that, we have the real measurement intervals, because into this phase, I can benefit of the steady way of the code. And let's see what we get during the runtime. Okay, okay, let's run the example. In regards with the number of iterations, I have like million. It's 10 million iterations. And what happened? The iterations for getting the square area took 8 seconds. One iteration took 5 nanoseconds. In case of rectangle, we've got pretty much the same, like 8 seconds for the entire time, and for one iteration we've got 5 nanoseconds. But what happened next? If we see this execution, we see that with the third execution, we've got a bigger elapsed time and a bigger iteration. This iteration took now 9 seconds. And if I continue with the real measurements intervals, I see that if I rerun again and compute the square area, I see now 10 nanoseconds for one iteration. In case of rectangle, 10 as well. And in case of right triangle, 10, it's the same. Let's see what happened, because this is the important thing. Let us understand what happened and why we have in the beginning, for example, here 8, and right after that it's 13, and here it's 14. In the beginning, when the program started to run, the just-in-time compiler optimized the square and the area, which was in fact a virtual method, became a monomorphic method and was inlined. That's why we got here 9 nanoseconds per the iteration and 8 seconds in total. When the compiler saw another implementation of the shape and it needed to do the area itself for the virtual call became a bimorphic call, and it was inline. But in case of inlining calls, the switch between these two implementation, it's based on the condition itself. What happened right after that? Because this is the case where when the time really differs. In this case, the just-in-time compiler saw the third implementation, and it has to de-optimize everything which was optimized previously, and it had to re-optimize it back. But in this case of calls, because in this situation we don't have any more a monomorphic call, we don't have any more a bimorphic call, we have a megamorphic call. In this case, this type of calls are not in light anymore. So after the second, starting with the third implementation, after the second implementation of a virtual method, the just-in-time compiler do not do inlining anymore. That's why here we have a worse elapsed time and an iteration that took longer. What we have here it's pretty much the same, because the code it's in a steady phase and we don't have any big differences between those two. That's why I told you, when we do performance testing or this kind of testing, don't rely on these warm-up phases. They might confuse you. It's not relevant for your testing. I'm going to move further, and I'm going to run it again with the pre-compilation, because with the pre-compilation, we'll see how exactly the just-in-time compiler does. Up to now, we understand what happens with all these method codes, but now let's see how the pre-compilation looks like. And if I'm going to enable the execution of my JVM with print compilation, I'm going to benefit of this output. What it means, in fact, it's a little bit verbose, but it gives us a really clue in regard to what happened during the runtime. This number, it's in fact a timestamp in milliseconds since the JVM has started. The second one, it's in fact the compilation ID. This percentage, I rather suggest to get rid of it. It mainly stands for on-stack replacement. It's a little bit too much. It's a little bit out of scope. It's just on-stack replacement, just that. We won't focus on this for today. What is important is this. This is the layer of our compilation, because I told you during the runtime there are many levels in the tiered mode from 1 to 4, and that's why we have here 1, 2, 1, 4, 3, and so on, from 1 up to 4. These are the just-in-time compilation levels, and let's see how it is, how it works in fact. Okay, let's take the do test. The do test method, the first time when I called the do test method for the square area, it became compiled, and it became compiled on the third level for the just-in-time compiler. What happened? Because my test continually invoked the method after it was compiled for the third level, it was profiled, and the just-in-time compiler realized that there is room of improvement, and it can be improved and compiled for the fourth, which is in fact for the C2 compiler. And that's why we have here the same method, and for the same method we have the fourth level. What is this made not entrant? And made not entrant, it's mainly saying that once I compile something and I realized that there is room of improvement. I have to make that piece of code that was compiled, I have to make it not entrant. It's just to invalidate it. And if it proves to be really not used anymore, it becomes zombie and it's collected. But in our case, it's just made not entrant, which means it's like a de-optimization part. And because we had the optimization part for the fourth layer. And of course, when we continued with another type of testing for the rectangular, the do test method became as well not rentrant and so on. And the process continues. It's the same thing in fact. That's why I told you when we are doing this kind of compilation with the second shape of the compiler with the C2 or in tiered mode, there are plenty of optimization and de-optimization of the code. And here, as you can see, when our real measurement starts, we don't have anymore this kind of fluctuation because the code is in the steady phase. The just-in-time compiler knows that I have 3 implementations for my virtual methods, and it doesn't make sense to compile and decompile to optimize and de-optimize it again and again, like we had in this warm-up phase. Okay, let's move on further and see the last point into my presentation. It's really a short one in regards with seeing the assembly code. I will show you how to check the assembly code based on what we've got during the runtime and the compilation. And for seeing that, you can, for example, run your application with these two arguments. But keep in mind that if you don't have the HSDIS library in your GRI environment, it doesn't work, in fact. So you have to do this library library creation in order to benefit of the assembly. And if I'm going to run it, okay, I'll see the assembly code, in fact. I can stop because the assembly code, it's hard to understand it, and it's a little bit too far from the purpose of this presentation. But just to let you know and to demonstrate to you how can we get from the source code through the bytecode, through the native code, and how to check the assembly code. This is mainly the presentation about. And I present you last point on my agenda is how to see this native code if there are some tools for it. And the answer is yes. There is a tool called JIT Watch. You can find it on the OpenJDK website. From there, you can also download the HotSpot sources under the OpenJDK project, because the OpenJDK and the HotSpot have the same code branch. And you can get it locally, you can compile it, and you can launch it. For our test scenario for today's presentation, I run, in fact, the same class as I did in Eclipse into this just-in-time watch, JIT Watch tool, and what I get here, it's really a nice view. I have it already launched just to preserve the time, because it takes a few seconds, and that's why I have it already launched. And since you launch it at the end, based on some logging that the JVM triggers, the JIT Watch assembles inspects, in fact, all the logs, assembles and displays them into this nice screen, in fact. And here you can switch the method. Here is my test method, do test method. Here, sorry, here it's the source code. Here, yes, here is the bytecode for it. And yeah, and here in the right screen is the assembly code, and only in this way we can understand how our code and the shape of it, the shape of the native code, what is the shape of the native code and how it was compiled in fact during the runtime execution process. I think I've covered all the topics I proposed for today. That was mainly my presentation. I'm waiting for your questions, and I kindly ask you to post them into the Q&A because it's more comfortable for me to search them and to check them. I don't see. Yeah. What is JIT acronym? So JIT stands for Just-in-Time Compiler. Just-in-time compiler, it's the compiler used in the hotspot. This is the just-in-time acronym. Another one is encapsulation versus inheritance also for performance. So encapsulation and inheritance are two different ways of achieving performance. To be honest, to achieve better performance, you don't have to do inheritance a lot. You have to avoid as much as you can, for example, virtual methods. But it defends, in fact, the OOP concepts and so on. That's why the hotspot itself was improved a lot into this. And encapsulation, of course, encapsulation it's in regards mainly in the overhead that comes into the stack. Because if I have to call something which is encapsulated, I can't do in any other way than pushing and popping the stack frame and the stack itself. Any other questions? Having all this knowledge, how useful was it for you in improving performance of the application? And do you have some war stories you have applied this knowledge? Only this knowledge, no, because this knowledge it's only the basics. Just to frankly speaking, you have to understand apart this knowledge. You have to understand the memory model and the way of garbage collections, because there it's the big bottleneck. The way of the garbage collection works. Mainly, I'll present that in another session. In regards to this presentation, what I can tell you is that take a look over your methods, and there is a really useful utility. It's called jar scan. Sorry. And if you are running your code, if you are inspecting it with the jar scan, it prompts you all the methods that are too long to be inlined. This is what you can do at this point. And of course, if you can, for example, to inspect them and to test it. Also, another thing that I insisted during the presentation, keep in mind for warm-up iterations, because the warm-up iterations are really important for your testing. And if you do some performance testing, you can't avoid them, because this is the nature of the hotspot. So jar scan, use it, and it will figure out all the method that needs to be reduced in terms of the size, because those ones prevents inlining. when it is mostly worthy to decompile and perform optimizations. Um, when it's mostly worthy to decompile and perform optimizations. To decompile and perform optimizations, this is the nature of the just-in-time compiler. This is the way it works. So it does a lot of optimization and de-optimizations. But of course, from the programmer perspectives, as I share with you during this presentation, it depends on how you structure your classes and the relationship between them. Because, for example, if you have a class with many implementations during the runtime, there will be a lot of optimizations and de-optimizations. So having this in mind, I can tell you the worst case is when you have one base class with plenty of optimizations, and during the runtime, you switch between those implementations. It's the polymorphism. This is the way of polymorphism and how it is implemented. And of course, in terms of the performance, polymorphism suffers. But the JVM with all these operations tries to reduce it. Does modifier final effects on just-in-time compilation? It really has no any connection. Maybe for example, how the bytecode is inspected. There is a CAJ, it's a class hierarchy analysis phase done, and if, for example, a method it has the final modifier, the compiler it's really sure that that method has only one implementation, and it's replaced by a monomorphic call. So in this sense, yes, it affects the optimization and the way it works, because the final method, for example, cannot be overridden. So we have only one. But in any other cases, no, they are not related anymore. Any other questions? You can also, if you don't have questions or those questions do not come through your minds right now, you can contact me to my mail, and we can keep in touch afterwards. Because I don't see any other questions posted in the channel.
So, Ionut, are there any other questions in the channel?
I've received from Florin Baku, there can be a question. Please, Florin, please ask me. I still haven't received your question. Yes, it is possible to use Java native code in other programming language. To use Java native code in other programming language. I'm not sure what you are referring to. You are referring, for example, to probably, I suspect you are referring once the code is at the assembly level, if you can reuse it. Yes, the answer is yes, it's just an assembly code. The only thing with that code is that be careful on the architecture you are running it, because this is the advantage of using the JVM. It adds an abstractization for the hardware layer. Once let's suppose you copy paste, just one sec. Let's suppose you copy paste this assembly code, okay, and you run it into another hardware platform. It might not work because it is not compatible. So the answer is, if you take the native code, yes, nobody prevents you to run it anywhere there. But the only thing is that the assembly code, because it's tightly coupled with the CPU registers for each architecture platform, you might get bigger chances to not work. So looking for other questions if you have. Still no questions. I don't have any other questions. Maybe that's it.
Okay, thank you, Ionut, very much for your presentation.
Thank you for you too.
Okay, guys, remember to vote for this report. And this concludes our DevLab conference for today. We thank you for your participation and we hope you've enjoyed the presentations. We would also appreciate your feedback, so please make sure that that you complete the feedback form so that we know how to tailor the future conferences we have to the needs and challenges that you face in your profession. And also remember to follow us on Facebook and LinkedIn to get news about our upcoming conferences. So without any further ado, I would like to wish you all a fantastic Saturday and see you next time.